Hey guys, this is the second part of our lecture on section 3.6, derivatives of log functions. Um, yeah, so if you're wondering what in the world is this guy doing, yeah, I am sitting here in my bathrobe, and that's because it is currently 3:07 in the morning, and I couldn't sleep. So I thought, hey, if you can't sleep, might as well do some math. So let's get another video out for you. So we left off last time talking about some formulas for how to take the derivatives of log functions. In the second half of this section, I'm going to talk to you about how to use logarithms to find some derivatives that would otherwise be somewhat complicated. So the technique that we're going to use is called logarithmic differentiation. And there's a procedure for how to do this. There are some steps involved to make sure that you're doing this the right way. So let me go ahead and write down the steps that you'll use going through this process. So the first step in using logarithmic differentiation is to basically take the natural log of both sides. So take the natural log of both sides, and then you're going to use some of those log properties that I mentioned in the last video to simplify. So we can say use log properties to simplify. And that's kind of the name of the game here. The whole idea in using logarithmic differentiation is to make things easier and simpler to differentiate. Okay, so that's our first step. Step number 2 is to differentiate. And we're going to differentiate both sides of our equation. And we're going to do that with respect to x. So we will take the natural log, we will simplify, and then we'll take the derivative of both sides with respect to x. And then the final step is to solve for dy dx or y prime, depending on the notation that you choose to use. So there's the process. And so what I'd like to do is walk us through a couple of examples to see how this is going to work. So let me get the process out of the way here. And we'll get into our first example. So example number 1 wants us to use logarithmic differentiation to find dy dx for the function y equals x to the 3/4 power times the square root of x squared plus 1, and this is all over 3x plus 2, and this is all being raised to the 5th power. Now, if I asked you to find the derivative of that, to just find dy dx, think about the techniques that would be required to do this. There would be a quotient rule. Within the quotient rule, you would have a product rule. And within all of it, there would be 2 different instances where you'd need to use the chain rule. And this thing would be very messy. There would be a lot of pieces to it, and it could be done, but it would not be the recommended way to solve this one. So this is where logarithmic differentiation is going to come into play. So the first step is to take the natural log of both sides. So I would begin by taking the natural log of y and setting that equal to the natural log of all this mess that I have here, x to the 3/4 times the square root of x squared plus 1, and this is all over 3x plus 2 to the 5th power, and I think we can just barely maybe make this fit. on the screen. And there we go. Okay. So we're going to take the natural log of both sides. So how can we use properties of logarithms to simplify this? Well, maybe this would be a good time. I reviewed them in the last lecture. I reviewed 2 of the properties. We're going to need, I think, all of them here. So why don't I just do a real quick review for you one more time of what they are in case you don't remember from the last video. So just a quick review. If you're taking the natural log of a fraction like this, the natural log of a over b, this is equal to the natural log of a minus the natural log of b. Or is this kind of like the quotient rule for logarithms? We have that if you're taking the natural log of a times b, this one I don't think I did last time, this is the same as taking the natural log of a plus the natural log of b. So there's the product rule. And then the last one is the power rule. So if you take the natural log of a raised to some power, I think I called it p, this is equal to p times the natural log of a. So those are the 3 properties that you're going to want to use. So when I said in the steps that you're going to use some logarithmic properties or rules or laws, whatever you want to call them, for simplifying before you take the derivative, these are the ones that I'm referring to. So in our example, we're actually going to find that we're going to use a lot of these, in fact. So we have on the left side of our problem, we still have the natural log of y. On the right side, okay, so let's start using some of these properties. The first property I'm going to use is that that first one I wrote down. I want to break it down so I don't have a fraction anymore. So I'm going to take the natural log of everything that's in my numerator. So that's x to the 3/4 times the square root of x squared plus 1. And from that, I'm subtracting the natural log of 3x plus 2 all raised to the 5th power. All right, so that's my that first property there. Now we can go further with this. If you look at the first natural log that we wrote, notice it's x to the 3/4 and then times this square root. And so that's a product. So that's like the second property I wrote down. And we can split that one up using addition. So this would become the natural log of x to the 3/4 power plus the natural log of the square root of x squared plus 1, and then minus the natural log of 3x plus 2, all raised to the 5th power. Okay, so that right there alone is pretty helpful in setting this thing up to differentiate. But we can go further with this because in all 3 of these, there's a power that can be moved to the front when we go to solve. So on the first logarithm you have the natural log of x to the 3/4. Well, that 3/4 power, that can be moved out front. So we could write this as 3/4 times the natural log of just x. On the second one, because it's a radical, it's not written with the power visible, but you guys should know by now that under the radical, the power is 1/2. So I can bring a 1/2 out front, and that would be times the natural log of x squared plus 1. And then on the last one, the last term, we have a power of 5. And so we can move that one out front and have 5 times the natural log of 3x plus 2. And all of this is equal to the natural log of y. Okay. So there we have things simplified out. So now what we want to do is we want to take the derivative with respect to x of every single term. So we're going to differentiate this thing. In fact, you can kind of think about it as taking the derivative with respect to x of all of this. And we're just going to go piece by piece. So let's start with the left-hand side. If I go to take the derivative of the natural log of y, well, we learned last time that the derivative for the natural log function is just 1 over whatever the input is. So this would be 1 over y But here's the problem. There's more to it than that. We're taking the derivative of a function containing y, but we're doing it with respect to x. So this is like that implicit differentiation. So if you guys remember that from before we went on the long hiatus there, the derivative for implicit differentiation is whatever the derivative is of the y function, but then times, remember we had to tack on that dy dx because of the chain rule. So let me put times dy dx. And again, that's implicit differentiation. That was 3.5 if you need to go back and look at that. Okay, let's work our way over to the other side now. So our first term is 3/4 times the natural log of x. Well, the 3/4 is a constant, so I can just leave that out front. The derivative of natural log of x, that's just 1 over x. So I get 3/4 times 1 over x. That takes care of my first piece. The second piece is 1/2 times the natural log of x squared plus 1. Okay, well again, I have this constant out front of 1/2. I'm just going to leave that there. I don't have to mess with that. The derivative of the natural log of x squared plus 1. Well, that's going to be 1 over x squared plus 1. But then there's a chain rule element here. So the inside portion of this logarithmic function, the input is x squared plus 1. So we have to remember to multiply by the derivative of that inside piece. So what would be the derivative of x squared plus 1? And hopefully all of you would know the answer to that question would just be 2x. Okay, so that's there because of the chain rule. All right, let's do the last piece. Minus 5 is the constant that stays out front. So it's a natural log function again. So it's going to be times 1 over my input. My input this time is 3x plus 2. So 1 over 3x plus 2. And then chain rule again. So times the derivative of the input. Well, the input here is 3x plus 2. So what's the derivative of 3x plus 2? And the answer to that is it's just 3. Okay, so we've taken all of our derivatives. So now what we want to do is we want to kind of clean this up a little bit. So just kind of looking at this, the side on the left, I'm not going to do anything with that right now. I'm going to leave that as 1 over y times dy dx. That side will change in a little bit here, but let me just see if I can't clean up the right side because there's a lot going on there. So the first term, the 3/4 times 1 over x, we can just multiply the fractions together and write that as 3 over 4x plus the second term. If you guys notice, there's a 1/2 out front, and then the last piece being multiplied on this middle term is a 2x. Well, the 1/2 and the 2, those can cancel each other out. So those pieces are gone. And so what we're left with here is the x at the very end of this thing. I'm going to multiply that up into the numerator, and I have x squared plus 1 in my denominator. All right, and then the final term, we just multiply these pieces together. Well, the 5 and the 3 will put a 15, and that'll go up here in the numerator. And this is over 3x plus 2. All right, that's as simplified as I want to make it. Now, if we really wanted to go crazy with this, we could try to figure out some kind of common denominator and put the pieces together, but that would be really, really tedious and not really necessary. So what do we need to do? We've used log properties to break it down. We've taken our derivative. The last step of this was to solve for dy dx. So dy dx is living over on the left side of our equation. The way we're going to get dy dx by itself is to make that 1 over y disappear. And the way to do that, of course, is to multiply both sides of our equation by y. So if I multiply both sides of my equation by y, in fact, I could kind of think of doing it like this, where I just put brackets around my whole equation and throw a y on the outside and say, okay, I'm going to multiply it here on this side, and then I'm going to multiply it, to the collection of everything on this side. Well, here's what that would look like when we do it. The y's would cancel out on the left side there, and we'd be left with just dy dx, which is what we want. And then this would be equal to y times, and then all this stuff. So all that stuff we just simplified, 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And we're almost done with this thing, right? We have dy dx by itself. The only thing that's left to do is we don't really leave our answer with y in it if we can help it. I'd prefer to have our answer, and it's common to see our answer in terms of just a single variable, and that variable being x. So the question is, how could we get rid of y and write it in terms of something where it just looks like x? And the answer is, if you go back to the beginning, if we kind of move this all the way back to the original problem, right here, we have what y is equal to. This is what y is equal to in terms of x. So what I'm going to do is I'm going to take that original equation and I'm going to substitute it in back down into our problem over here. So instead of writing this here, I'm going to substitute it with that piece I just circled and have my final answer just being in terms of x. So our final solution to this is going to be dy dx is equal to, we have x to the 3/4 power times the square root of x squared plus 1 over 3x plus 2 to the 5th power. And then all of that is multiplying everything here in the brackets. So 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that is your final solution. Okay, so there we go. So kind of a lot going on in that problem. In fact, it might be worthwhile if we just kind of recapped what we did just really quickly here. So if I go back to the beginning, we were tasked with finding the derivative of that function that is circled in red. And we mentioned at the beginning that, sure, it's possible to use quotient rule and product rule and chain rule again and power rule 3 times. And it's going to be a hot mess, right? Even more so than me at 3 in the morning in my bathroom recording math. We don't want to do that. So, so what we do is we take the natural log of both sides. And by doing that, by applying the natural log on both sides, we're able to break this thing down from being one gigantic messy function into 3 smaller, more manageable functions. So we used all those properties there in blue. So make sure you have those in your notes for sure, and maybe even highlight them or do something where they're going to stand out so you can refer back to them as you need them. And we used all those different properties to simplify down our function. And what our function was here in the red brackets. We broke it all down, and then we took the derivative of each of these pieces independently, and that each one by themselves wasn't too bad. And then once we took those derivatives, we simplified them as best we could, and then we just solved for dy dx, which just required us to multiply both sides by y. And then the last thing was just to do a quick replacement and take y out and replace it with the original equation, so our entire answer was just in terms of x. Okay, so that was our first taste of using logarithmic differentiation. So I want to do one more of these with you, just for some practice, and then I'll leave it to you to practice some more with the problems outlined in your syllabus. So example number 2 is, again, we're using logarithmic differentiation to find dy dx. This time, we have the equation y is equal to x raised to the square root of x. X raised to the square root of x. Now, on this one, we're not allowed to use the power rule on this. So if you're thinking, well, couldn't you just bring the square root of x down and then replace it by 1 less? No, that doesn't work, because that works when our power is a constant value. It's just a number Here, our power is a variable, and it's the variable that we're differentiating with respect to, in fact, and the rules don't fit this type of situation. So the only way we have that we can deal with this is to use logarithmic differentiation. So our first step is to take the natural log of both sides. So we would write the natural log of y is equal to the natural log of x raised to the square root of x. And this time there's only one of the properties that we're going to be dealing with. And that property is the power rule, which is going to tell us that we can take that power of the square root of x and we can move that down to the front. So we have the natural log of y is equal to the square root of x times the natural log of x. Okay, so now it's simplified down for us, and this is going to be something that we can deal with. It's square root of x times the natural log of x on the right side. So when we go to take the derivative in a moment, what we're going to be using is, I hope you would see it as the product rule would be the thing that would make sense here. So on both sides, we are differentiating with respect to x. Okay, on the left side, the derivative of the natural log of y. We did this in the last example. It's 1 over y, but then because we're differentiating with respect to x and our function is in terms of y, that's implicit. The chain rule tells us times dy dx. Okay, so that takes care of the left side. On the right side of this, we have the square root of x. Now, that piece, remember, is just x to the 1/2 power. So if it's easier for you to think of it like that when we're differentiating, that's fine. So the product rule says take the derivative of the first piece. So the first piece is x to the 1/2. So if I take the derivative of that, I'm going to get 1/2 times x to the minus 1/2. So there's the derivative of the first piece. Now I multiply that by the second piece, so times the natural log of x. And now the rest of the product rule says plus. And now this time we leave the first piece alone, so I'm just going to leave it in its radical form as the square root of x. And we're going to multiply this by the derivative of the second piece. Well, the second piece is the natural log of x, and the derivative of the natural log of x is 1 over x. All right, so there is our derivative. Now, what can we do to make this maybe look a little bit nicer? I just kind of want to work with the right side here for a moment. So 1/2 times x to the minus 1/2. We've done that one enough times. I think you guys all know that that's 1 over 2 square root of x, right? If we get rid of the negative exponent and then put it back in radical form. And then times natural log of x. And then on this one, we can put the pieces together and write it as the square root of x over x. And let's see, can we do anything else with this to make this look a little bit nicer? We can multiply the pieces here on the left term by writing natural log x over 2 root x. And on this guy, the square root of x over x, well, that's going to simplify down to 1 over x. 1 over the square root of x. I swear I can do math, I promise you. It has nothing to do with the fact that it's now past 3:30 in the morning. 1 over the square root of x. If you're wondering, okay, how is he getting that? Just remember that, let me just come off to the side here, I'll put this in a different color. Square root of x over x is the same as x to the 1/2 over x to the first power. And if you remember your exponent rules, we can subtract 1 in the bottom, subtracting the half up top becomes 1/2. So I get 1 over x to the 1/2 power there, which is the square root of x. Okay, so that's where that came from if you're kind of scratching your head wondering what's going on there. On the left side, we still have 1 over y times dy dx. Okay, we're almost done. What needs to happen next is we need to, just like we did before, I want to multiply on both sides of my equation by y. And that's going to cancel the 1 over y on the left and leaving us with just dy dx, which is the thing that we're solving for right now. So we're going to get dy dx on the left. And then on the right side here, we're going to get y times everything that was already there. So natural log x over 2 root x plus 1 over the square root of x. And then just like before, in the last example, we're going to make a quick substitution to finish this thing off. Remember, when we started the problem out back at the beginning, y was given to us to be x to the power of the square root of x. And we want to substitute that back into our final solution. So down here, we're going to write dy dx is equal to x raised to the square root of x power. And then we're going to multiply all of that by the natural log of x over 2 root x plus 1 over the square root of x. And that's as nice as I care to make this one. And there is logarithmic differentiation. So there you go. There wasn't too much left for us to do in that section. I hope you guys do okay with this. It can be a little bit tedious, especially if you're not up to date with those log properties. You might need to refresh on those a little bit before you really feel comfortable with this stuff. But you'll get through it. If you got questions, you guys know how to track me down. We can talk about them in class. We can talk about them in office hours, whatever you guys need. So anyway, that's it. And I will see you next time.